Okay, today we're going to talk about how you simplify square roots. Also, how can you multiply and divide square roots. Okay, make sure you understand and remember what a square root is. Okay, a square root, when you have a number inside a square root, for instance, let's just say we said x squared, you got to realize what's happening is whatever that number is that it's being multiplied by itself. Okay, because remember, if I had x squared when we did the distance formula, we were trying to find the distance of something, or when you do the Pythagorean theorem, if I had a number, say I said x squared equals 16, well, how would I get x by itself? Well, what's happening to x right now? Well, yeah, x is being squared, so to undo squaring, you have to take the square root, and if you do something on one side, you have to do it on the other, and so therefore you would have x equals 4, because the square root of 16 is 4. And that's the first thing I want to talk about, is make sure you know your perfect square numbers. For instance, the square root of 1 means you go 1 times 1, so the square root of 1 is 1. The square root of 4, you get it by going 2 times 2, so the square root of 4 is 2. The square root of 9, well, 3 times 3, so the square root of 9 is 3. You have the square root of 16, which is 4 times 4, so the square root of 16 is 4. How about the square root of 25? What number can you multiply times itself and get 25? That's right, 5. So the square root of 25 is 5. Now, for right now, I won't do the next 5, but you should know them. The square root of 36 is 6. The square root of 49 is 7, and so on. Okay. But there are some rules with your radicals. So a couple things. Let's look at some of these definitions that they have right here, putting the radical in simplest form. Okay, the radicand has no perfect square factors other than 1. In other words, a radical or a square root is not simplified until the only factor that the number has left is a perfect square of 1. In other words, the square root of 1 is 1 times 1, or 1. Okay. Also, the radicand has no fractions. In other words, and this is important, you can never have a square root in the denominator. It can't be in the bottom of the fraction. Ever. You can never leave it there. Okay? So, we have some of these problems right here, some practice ones. Okay? And so I'm going to go ahead and do the first 3 with you. Okay? This first one here, negative square root of 20. Well, first of all, we're not going to do anything with that negative. It's sitting there. But what we're going to do is we're going to try to find some factors. We're going to try to find some numbers that when you multiply a number times something, you get 20. But what we're looking for, we're not just looking for anything. We're trying to find a number that is a perfect square number that's a factor. Okay? For instance, I have these factors over here. I have the first 5 perfect squares. Well, let's think about it. What factors of 20? You got 2 times 10. You have 4 times 5. Well, isn't 4, when a 4 is in the square root, see where I'm circling the red right here? Isn't the square root of 4 a perfect square? So I have negative square root of 4 times 5. Well, now this thing still equals 20 inside that, underneath that radical, okay? But this 4 is a perfect square number. So what did we say the square root of 4 is up here on the far left in blue? We said it was 2. So we have the square root of 4, so a 2 is going to come out. So what we have is we have negative 2 times the square root of 5. And so that is that radical, the negative square root of 20. That's it simplified, negative 2 square root of 5. Okay, let's look at number 2. Notice how they have a fraction inside this radical. I need you to understand that anytime you have a fraction in a square root, it's the same thing as writing the radical like this. Okay, the way the problem is originally written up here in red and how I wrote it in black, those mean the same two things. So that would be the first thing I would do, is I'd go ahead and take this thing that's in the red circle and break it apart. Okay, well, if you remember up here above, I said, okay, you can never have a square root or a radical in the denominator, and look what we have right here. We have the square root of 3 that's in the denominator, or the bottom of the fraction. Well, it can't be there. So the way that we're going to get rid of it is, and it's simple, you just are going to multiply by that square root on top and on bottom. So we're going to take the square root of 3 that's on bottom, and we're going to multiply it by itself as a fraction. And now it's got to multiply straight across. Well, when you multiply the square root of 3 times the square root of 3, I'm going to come over here to the left a little bit. That's the same thing as saying the square root of 3 times 3. This thing here and this statement here is the same. Well, what is 3 times 3? That's right, it's 9. And what did we say the square root of 9 was? Oh, the square root of 9 was a perfect square, and the square root of 9 is 3. So anytime you multiply a radical by itself, what happens is the radical disappears, and you're just left with the number itself. And then on top, I can multiply those two things. 34 times 3 is 102. And 3 and 34, those are prime numbers, or they don't have any factors that are perfect squares. Like 34, you could get it by going 2 times 17, but neither one of those numbers are perfect square numbers in a radical. So this is that answer simplified, the square root of 102 over 3. All right, let's look at number 3, and I kind of wrote on top of it, so I'm going to rewrite that problem. Notice the issue right here before we even get started. What's the problem with 12 over the square root of 5? I'll give you a hint if you watch the blue pen. That's right. You can never have a square root in the denominator or the bottom of the fraction. So this square root of 5 can't be there. So to get rid of it, we multiply by the square root of 5 over the square root of 5. Well, multiply straight across. And so now I have 12 times the square root of 5. Okay. And then on bottom, well, the square root of 5 times the square root of 5 is 5. And the square root of 5 that's on top, it's simplified because 1 times 5, well, 1 is the only common factor that's a perfect square, so that's simplified. And then I look at 12 and 5. For instance, if you would put a pin over the square root of 5 right here, in other words, if you would cover that up and you just had the fraction 12 over 5, well, would 12 over 5 simplify any? Are there any common factors between 12 and 5? No, there's not. And so this thing is my final answer. Okay, a couple properties here. The product property. Remember what product means. Product means to multiply. So we got the example here, the square root of 45. Well, let's think of some factors of 45. Now, there's several factors of 45, but again, remember, you want to try to find perfect square factors. For instance, I know that 15 and 3 are factors of 45, but neither one of those numbers are a perfect square number. But how about 9 times 5? And why is 9 helpful? Well, if you remember up here above, right here, remember what the square root of 9, when it was inside a radical, the square root of 9 is a perfect square number. So, go back. If I take and break 45 apart and say the square root of 9 times 5, well, it still equals 45, but this 9 is a perfect square number. What is the square root of 9? That's right, it's 3. So a 3 comes out, and the square root of 5 is simplified, so it stays in, and so that is my answer. Okay. The quotient problem. Remember we said we would do anytime we had a fraction in the square root. We said that we would take the square root, and we would separate the two numbers. Now, in this one, the square root of 49, remember we said we couldn't leave a square root in the denominator, and our normal rule, if you look over here where I'm drawing the blue arrow, we would multiply by that square root over itself. But we don't need to do that right here because this is a perfect square. Can't you go 7 times 7 and get 49? Isn't the square root of 49 a perfect square number? That's right, it is. So I have just 7 over the square root of 6. Or square root of 6 over 7, I'm sorry. All right. So let's do a couple here together over here. And we're going to keep practicing. We're going to simplify these radicals. I'm going to do all these with you, so just kind of stay along with me. The first one, the square root of 24. Again, you have several factors of 24. You have 3 times 8, you have 2 times 12, and you have 6 times 4. But there's only one group there that has a factor that's a perfect square factor, and that is 4 times 6. Because remember, this square root of 4 is a perfect square. Well, what is the square root of 4? It's 2. 6 is simplified, and so 2 times the square root of 6 is my answer. Go to number 5. Okay, I'm going to leave that square root of 2 out there. Let's break down 48. Let's think of the factors. You have several factors. You got 4 times 12, and 4 would do some of it, but doesn't 12 also have another 4 in it? Because 4 times 3 would give me 12. So there's probably something bigger. How about 16? How about 16 times 3? Okay, isn't 16 times 3 48? Well, yeah, it is. Well, what is the square root of 16? Well, it's a perfect square. It's 4. So a 4 is going to come out. But when that 4 comes out of the square root, it's going to be multiplied to this negative 2. And so what is negative 2 times 4? It's negative 16. And I still have the square root of 3 inside. So the answer here is negative 16 times the square root of 3. All right, I want you to do number 6 and number 7 on your own. And then when you have an answer, raise your hand and let the sub check your work and see if you got it correct. All right. So now I'm going to do 8 with you. Okay, again, you got a fraction and a square root. So remember what we said to do. We were going to go ahead and separate the fractions. Okay, because what I've just written in red is the same thing as what is originally written. Okay, and we remember we can't have a square root in the denominator. Well, this square root of 4, though, happens to be a perfect square number. So what is the square root of 4? That's right, it's 2. And the square root of 3 is already simplified, and so that is my simplified radical. So what I want you to do is I want you to do number 9 on your own. When you think you have an answer, raise your hand and have the sub come by and see if your answer is correct, or if you need help, they will help you. Okay, so moving on to the second page. Okay, performing operations with radicals. Probably the best, not the best. Use your rules that you use when you add, subtract, multiply, and divide with variables. Remember, when you would add and subtract with an x or a y, to combine those to add them or subtract them, didn't you have to have like things? In other words, if you had 2 x's and 3 x's, you could add those together. But if you got 2 x's and 3 y's, you can't add those together. So remember, it's like terms. Well, same thing with radicals. You have to have like radicals to add. For instance, they've got an example just like I'm talking about. Notice I have 3x plus x. Well, that's just like going 3 plus 1, which means I have 4 x's. Well, the same rule applies with radicals. For you to add or subtract radicals, they have to be like radicals. And if you notice, both of those statements there both have the square root of 5. So over here I have 3 times the square root of 5, and it's being added to 1 times the square root of 5. Well, what's 3 plus 1? It's 4, and so I have 4 times the square root of 5. Okay? Well, let's do some together. Let's look at number 10. Okay, first of all, do we have like terms? Do we have like radicals? And we do, that both of them have the square root of 7. So, look at the outside number, 3 and 2. Can I combine those two together? I sure can. And 3 plus 2 is 5. And then I have the square root of 7. And I'm done. Okay. All right, I want you to do number 11 and number 12 on your own. If you get an answer, or if you get stuck, raise your hand, and the sub can help you. They have the key. Okay. All right. So number 13. They want the exact perimeter of a rectangle whose width is 4 times the square root of 5 and the length is 5 square root of 9. So I'm going to give you a visual. We're going to draw a rectangle over here. And so we have one set of sides. Remember, in a rectangle, the opposite sides are congruent because it's a parallelogram. So we got 4 square root of 5. And then the other set of opposite sides are 5 times the square root of 9. Okay? Well, how do you find the perimeter of an object? That's right. You add all the sides. So that's what we're going to do. We got 4 times the square root of 5 plus the other 4 times the square root of 5 plus 5 times the square root of 9 plus 5 times the square root of 9. Well, so we're adding, so remember when we add radicals, we have to have like things. So let's look at our radicals. Well, these two radicals are the same. They're both the square root of 5. And these two radicals are the same. They're both got the square root of 9. So we can add the two that are in black, and we can add the two that are in blue. And so what our final answer should be, well, what's 4 plus 4? Well, it's 8. So I got 8 square root of 5 plus, now I add my other things. So I got 5 plus 5, which is 10 square root of 9. And that is my final answer. Okay. Now, we talked about rules with the radicals, that it was just like with a variable, right? You can add like terms, right? Well, when you multiply with variables, for instance, if I have 2x times 6x, well, remember I can add those. I can multiply, and it doesn't have to be like, okay? Because 2x times 6x, well, that's 12x squared. Or if I change this to y, I can combine that because I'm multiplying. Multiplying is different, because I would have 2 times 6, which is 12xy. I don't have to have like things to multiply. Well, the same rule applies with radicals. Okay, so I don't have a lot of room to do this example right here. Okay, so I'm going to bring it down here a little bit. So I'm going to rewrite 2 times the square root of 3 times 5 times the square root of 2. And you don't have to do it this way, but it does work out a lot nicer. First thing, I'm going to go ahead and multiply just my numbers. So 2 times 5, well that's 10, right? 2 times 5 is 10. And then I'm going to go ahead and multiply my two square roots. Well, what is 3 times 2? It's 6. So I have 10 times the square root of 6. Now I always need to look at my number that's in the radical. Is it a perfect square? Well, the factors of 6 are 1 times 6, and 2 times 3. Well, the only number out of that is a perfect square is 1, so this right here is my final answer. So let's do some together here. Again, I only have 5 times the square root of 2 times the radical 6, so nothing's going to move the 5, so it's just going to stay. And then what's 2 times 6? Well, it's 12, right? And then I need to see if there's any perfect square factors. Well, let's think about what numbers we can multiply and get 12. 1 times 12. 2 times 6, and 3 times 4. Are any of those perfect square numbers? Yeah, square root of 4 is. So, we know we've got to break it down. Okay, so 4 times 3, so it still equals 12 on the radical, right? And what is the square root of 4? It's 2. So a 2 has to come out, but when that 2 comes out, isn't it going to be multiplied to 5? So 2 times 5 is 10, and I'm still left with that 3, and so the final answer is 10 times the square root of 3. Number 15, 3 times the square root of 11. Well, first of all, the square root of 11 is already simplified. That 3, it's not going to go inside, so really that answer is just that. It's no big deal there. Number 16, I'm going to go ahead and multiply those two things together, so I still have the 4. 6 times 12 is 72. So let's think about our factors of 72. And the bigger factor we pick, the less work we have to do. And yeah, 9 is a perfect square number and it is a factor. So is 4. But I need to go bigger. And really, 36 times 2. Because 36 times 2 is 72. Well, isn't 36 a perfect square number? I mean, let's think about numbers that we multiply and get 36. Okay, isn't 6 times 6 36? Yeah, so the square root of 36 is a perfect square number. So a 6 is going to come out. When that 6 comes out, remember it's got to be multiplied to 4. So what is 6 times 4? It's 24, and I'm still left with the square root of 2. So 24 times the square root of 2 is my answer. All right, I want you to do number 17 on your own, and when you think you have an answer, raise your hand and see if you get it right, and then we'll talk about number 18. Okay, number 18. Uh, Find the area of a square whose side length is 3 square root of 4. Well, remember, how do you find the area of a square? Well, the way you find the area of a square is you just go side times side, right? So, all of our sides are 3 square root of 4. So, what we're going to do is we're going to go 3 square root of 4 times 3 times the square root of 4. Now, at this point, it doesn't matter how you do it, but I'm going to multiply those two things together. What's 3 times 3? It's 9. And then I'm going to multiply my two square roots together. Well, what's 4 times 4? And 16. So I have the square root of 16. All right? Well, isn't the square root of 16 a perfect square number? Yeah, it is. And so the square root of 16 is just 4. And so I still have this 9 out here. So what's 9 times 4? It's 36. And so this square has an area of 36 square units. Okay. All right. So that's all the notes. The big thing to remember with variables or with radicals is you can't have a square root in the denominator. Okay. Also, when you add radicals, use this. Anytime you mess with radicals, use your variable rules. You can't go wrong. In other words, when you add and subtract, they have to be like things. And then when you multiply, it's the same rule. You multiply anything. So the assignment is attached to the back of the notes. Go ahead and do all that, and this assignment will be your next class meeting, which would be next week, and I should be back, and we'll talk. I'll see you guys later.